So let's then look at the behavior of a monopolist under price cap. So we now know what we would like this monopolist to do. So we would like him to invest as soon as prices hit this PW that we just computed. But we suppose we cannot just order the monopolist to do so, but the only instrument that we as a regulator have at our disposal is to tell the monopolist, well, listen, you do what you want in terms of investment, but you are not going to be allowed to ask prices which are higher than a given price cap. So this is actually the question that's then analyzed by Dobbs. So we would like this monopolist to speed up his investment compared to the unregulated case, in which it would just wait until prices hit this PM value. So the question is, can we indeed make the monopolist to invest earlier by imposing such a price cap, and in particular, what's the optimal level then for this price cap to get as close as possible, perhaps even at the welfare maximizing level. So let's look at the price cap. So what the regulator does is it says, well, P bar is the maximum price you can charge. So whatever you do, that's okay, but you can never charge a price which is higher than some given P bar that I'm going to tell you now. Now, of course, the first thing to note here is that we should have this P bar being lower than the PM, right? The price level at which the monopolist would itself invest, because at PM the monopolist would never allow actual prices to go higher than PM anyway. It would invest in new capacity as soon as prices hit PM, driving prices down again. So P bar bigger than PM or at PM does not make any sense, because then we basically are doing nothing that the monopolist would not already be doing himself. So we are basically concerned about thinking about what happens if we set a P bar which is lower than that monopoly price level PM. So we have to figure out what's the effect of such a price cap on the profit flows that the monopolist can get. So now its profits are going to be might be a bit lower, because you are sort of constrained as a monopolist. You're constrained to how high you can set prices. And because profits is going to be different, of course also the investment behavior is going to be different. So we want to figure out what's the new investment behavior by the monopolist when it's exposed to such a price cap. So in order to solve that, of course, we again have to solve this real option problem. So we again have to identify Bellman equations for different regimes. So and of course we first let's fix again our capacity K, and let's wonder what's going to happen for different levels of this uncertain parameter theta. Well, first thing to notice is that if theta is very low, so theta is the demand level, remember this factor maximizing, multiplying demand. So if theta is really low, it is very low demand, what would the monopolist want to do if it were unconstrained? Well, it would definitely set it would use all its capacity, of course. It would like to set a price theta times k to the power minus gamma, and in fact if theta is really low, it can just do so. So as long as theta times k to the minus gamma is smaller than this allowed price cap level P bar, well, nothing is preventing this monopolist from behaving in its own optimal way. So it will just get the total profit level, sets its prices to the price level that it would like to, and would get a profits equal to total revenues, that price times quantity K. So it would just get a profit flow of theta times k to the power 1 minus gamma, as if there were no price cap at all, actually. But at some point, if demand is growing, well, at some point the price that it would like to set is going to grow, right? Because the price it would like to set is this amount here. So as theta is going up, at some point you will hit actually this price cap level, and beyond that you can actually no longer increase prices, because you are hitting this price cap level. So as soon as theta is above that particular level, so as soon as theta times k to the minus gamma is above p bar, what's going to happen is, well, my profits is, well, what can I do? I would like to set a higher price. I'm restricted actually. I can only set p bar. Well, that's what I'll do. I'll set my price equal to p bar as a monopolist. That's what, all that I can do to maximize my profits. The quantity that I'm selling, of course, is still k. I'm selling my total capacity. So the total profit flow that I can realize here is p bar times k. It doesn't actually depend anymore on theta. So in this regime, when theta times k to the power minus gamma is above p bar, there my profit level is something which is independent of theta. Well, as theta keeps on growing further and further, there will at some point, we will get to some theta level, some theta star if you wish, which corresponds to a price level p star, at which this monopolist will say, well, at this point I'm going to invest. I can actually earn a little bit more by investing, because then I'm going to raise k, and so I cannot raise p bar, but I can raise k, and that's might actually increase my profits, and I'm going to do that as soon as I will reach this investment threshold, which I again call p star. So when that threshold, well, the corresponding threshold will be theta star, when that's reached, this monopolist is going to invest. And we need to find, of course, what is the threshold. It's something that we need to figure out. So we need to figure out what p star, or in other words, what theta star as a function of k will be. So in a picture it looks like this. So if theta again is fairly low, so below this parameter, which let me just call that for convenience theta bar, so it's the theta level at which I would like to set a price exactly equal to p bar, price cap level. I, as a monopolist, am not constrained. I just ask my profit maximizing level, and getting profits theta times k to the power 1 minus gamma. So that's in this regime. I'm not investing here, of course, in capacity. I'm just capturing this flow of profits over here. If I then pass this threshold theta bar, I'm still not investing, but something is going to differ, because the profits that I'm capturing at this point are going to be fixed at p bar times k. I would like to go higher, but I cannot, because that would exceed, would lead to prices that would exceed this price cap level. And if theta goes even further and further, at some point I hit an investment level theta star, at which I prefer to actually invest in new capacity to expand this k to a slightly bigger k, make a higher flow of profits, and we want to figure out what the theta star is. So essentially we have these two different regimes, regime 1, regime 2. So in regime 1 we have a Bellman equation, which will be waiting until we reach regime 2 essentially. So in this regime 1, the profit flows are going to be equal to theta times k to the power 1 minus gamma. That's these profit flows, plus these two terms that we know, these derivative terms. And we can actually solve this equation. And we have to be aware that theta equals 0 is part of that regime. It's one of the boundaries of this regime actually. And because we don't want the total profit levels W here to blow up to infinity, we are going to exclude actually the negative power. So that's why we only see this positive beta 1 power of theta appearing here. And of course, this again is the growing perpetuity that corresponds to profit flows that are theta times k to the power 1 minus gamma. So in this first regime between theta equals 0 and theta equals theta bar, W takes this particular form. Well, that's no longer the form that W will take in the second regime, because here the flow of profits is going to be different. So again, in the second regime, we also have a Bellman equation, but now with this different flow of profits. And particularly this flow of profits is not dependent anymore on theta. It's just a constant. So within this regime, we can actually write down again what the solution is to the Bellman equation that's relevant for thetas in this regime between theta bar and theta star. And the Bellman equation looks like this, and the solution to that Bellman equation is going to be, well, this thing is a constant, so this will yield us this perpetuity now rather than the growing perpetuity expression. So this constant p bar times k divided by r, because it doesn't, the constant, its constant doesn't depend on theta, so constant forever gives me this perpetuity of cash flows. So that's the particular solution here to this Bellman equation. And we add to that again these general solutions to the homogeneous Bellman equation, if you wish. But now, well, we're in this regime between theta bar and theta star, so neither theta equals 0 is part of that regime, nor theta going to infinity is part of that regime. So we cannot rule out either the positive power or the negative power. So in general, both these two powers will be present here in this expression, each with their own coefficient. And of course, this coefficient, compute this for a fixed k, but for a different k would have a different, same form but different coefficient. So b and c, these coefficients are actually functions of k as before. So now we have solved these general solutions to the Bellman equation in regime 1 and in regime 2. And what we now need to make sure is that we are going to tie these two solutions together at theta bar in a nice, smooth and value match continuous manner, and also that we are going to actually look at this investment bit here at theta star. So in other words, we need to figure out what is A of k, what is B of k, what is C of k, and what is theta star. So 4 unknowns. So at theta bar again, we will have value matching and smooth spacing, so that will give us two equations. And furthermore, at the investment threshold level, theta star, we will again have the value matching, but now in terms of the marginal increment in value as we increase k a bit should equal marginal investment costs, like in Pindyke. And also, of course, for optimality, the derivative of that thing with respect to theta should equal 0. So that's two more equations. So we have 4 equations, 4 conditions, and we also have 4 unknowns, so we might hope to be able to solve those 4 unknowns by using those 4 conditions. So what do these conditions look like if we plug in what those values, those value functions are? Well, at theta bar, we want to make sure that the left-hand side matches up nicely with the right-hand side, so not the derivative itself, but not the derivative with respect to k, because k is going to be constant all over this place, because the only place at which you're investing in k is over here. So here k is just constant, it's fixed at k. So we want the w itself to be value matched across this boundary, and we also want w to be smooth across this boundary. So if you remember back a bit to this Murto and Nasa paper, this looks actually a bit like this this case in which we looked at the temporary shutdown of operations, suspension of production. Same kinds of equations that we are solving here. So we're value matching there, so the left-hand side evaluated at theta bar should equal the right-hand side evaluated at theta bar, and also we have smooth spacing, so the derivative of the left-hand side, so the derivative with respect to theta of this thing, we have the theta vanishes here, the power goes down by 1, and we get the beta 1 in front of this, so that's the left-hand side over here. Same way over here, this first thing derivative of this constant, not theta dependent, gives 0, it's not there, and the derivatives over here yield these two terms, beta 1 times b times theta bar to the power beta 1 minus 1, plus the beta 2 factor times c times theta bar to the beta 2 minus 1. So these are the value matching and the smooth spacing conditions at theta bar. So there are 2 equations already. We have 3 unknowns already in here, so we cannot solve them completely. For that we also need to figure out the other boundary conditions, the boundary conditions at theta star. And here, these are the boundary conditions that correspond to optimal investments. So here we need indeed that this the derivative with respect to capacity should equal marginal cost of investment, and the theta derivative of this marginal W should equal 0. So if you work that out, well, on the left-hand side here, or this function basically is the relevant function here, because we're looking at this boundary here, the theta star boundary, so looking at this particular function. So take the k derivative for the value matching equivalent here is, well, p bar divided by r plus these two derivatives with respect to b and with respect to c should equal I, should equal the cost of investment, the marginal cost of investment. And the theta derivative of that thing, well, this first bit is going to vanish, but we do have the theta derivatives of these option powers, and they should equal 0. So these are two further equations. So now I have 4 equations. So remember, we had those 2 equations here from value matching smooth spacing at theta bar, involving A, B, and C, the 3 things that we want to know. And we here have the value matching and smooth spacing at the investment threshold where k is going up, and these involve B prime, C prime, and theta star. So the same B and C functions, but also theta star. So 4 unknown things. These functions B of k, C of k, and also A of k, and the theta star, and we have these 4 equations. Now this is quite a job actually to solve these 4 equations in 4 unknowns. It can be done analytically, and actually Dobbs does this, but I'm not going to ask you to actually reproduce this on your exam. So you might try to do this, to exercise this a bit. It's a bit tricky, so have a look at what Dobbs does if you don't manage to do that. But again, this is not something I'm going to expect you to be able to do by yourself in the exam, so don't worry about that. So Dobbs does it, kudos to him. So what he finds is, well, the investment threshold, which is the thing that we are particularly interested in, the theta star, is such that theta star times k to the minus gamma, so in other words, the price at which we will make the investment p star, we can express that rather nicely as p bar times this whole fraction here to the power 1 divided by beta 2. So what can we see already when we look at this threshold? Well, this threshold p star is going to be bigger than p bar, because if you think a bit about this whole fraction here to a negative power is going to be a number that's going to be bigger than 1, because we know that p bar is going to be smaller than pm. So by virtue of p bar being smaller than pm, this thing in the brackets is going to be smaller than 1, but we're raising this to a negative power, so this whole factor is going to be bigger than 1. So if we indeed find that there will be this regime 2 in which we are in between p star and p bar, at which we will be waiting to invest but just not adapting our price will remain fixed in that regime at this threshold level, at this regulated level, at p bar, at the price cap level. What we can also see is that as soon as p bar equals, so if p bar gets as low, I should say, as Ri, we have a 0 over here, the 0 to the negative power, so 1 divided by beta 2, that's the negative power, that should blow up. So we should see in our graph, if we're going to look at the next slide, the graph of p star as a function of p bar. Well, if p bar gets lower and lower and reaching ultimately R times I, then we should see this p star blown up. So we'll see that in the picture. And also if p bar goes up all the way to pm, so to the monopoly price level, and then what we have here in the brackets is the same in the numerator as in the denominator. If p bar is equal to a pm, so then this whole thing in the brackets is equal to 1, so 1 to any power, to the negative power as well, is just going to be 1. So as soon as p bar is going to be equal to pm, but then also p star is going to be equal to pm. But so, okay, what this result in general says, if the regulator sets some price cap at P bar, well, then P star, this expression over here, is going to be the investment threshold, the price level at which the monopolist is going to invest. So we want to just explore this in words a bit, but let's look at this in a picture, and we are then going to ask, how should we set this P bar? If you're the regulator, we have the right to choose this price cap P bar, and we rather make sure that we choose this price cap in such a way that the threshold P star, so the threshold at which this monopolist is going to invest, is as close as possible to the welfare maximizing level PW that we computed before. So let's have a look at the picture. So here's the picture. So what is this? So on the horizontal axis we have this choice of price cap that we have at our disposal, so we can choose as a regulator what's P bar. But if we give the monopolist this price cap, then the monopolist has the right to determine at what level am I going to invest. So the threshold level will be on the vertical axis, and in particular this function that we just computed, the P star, will be the threshold level at which price would go, or at least the price that the monopolist would like to set. So the theta star essentially it's commensurate with that particular price. So we would like to set actually a price which is as high as this drawn black line. That's the P star level. Of course, he is restricted. He can only set the blue line, but we have to wait until he would like to set a price equal to this P star, so the black line. That will be the moment at which this monopolist is going to make the investment. So theta has to grow until the optimal price for the monopolist would be this black line, even though he can only price up to the price cap level, the blue line, which is this horizontal blue line, which is the cap level. Sorry, the dashed line, I should say. The dashed line, that's the price cap level. So that's P bar. So this is the price cap level for different values of the price caps, and we are going to make the investment as soon as the optimal price for the monopolist would have been the drawn black line. So then the other two lines, the blue and the red line, are, well, the red line was our original unconstrained monopolist price level. So if we don't implement any price cap level, well, prices will grow until the red line, and that will be when the monopolist is going to invest. And vice versa. The blue line is the welfare maximizing price level. So we would like, if we are to maximize the total welfare, that's the price that we computed, we would like the monopolist to invest already when prices hit the blue line. Well, we can immediately see, well, that's never going to happen. So the price at which or the theta, I should say, the theta star at which price would have been this black line, and that's the level of theta at which the monopolist is actually going to invest under this price cap level. So we can never get the monopolist to invest all the way at the optimal PW level, but we can get close. So we can get close enough by, this, of course, this is the minimum level at which we can make this monopolist invest at that, to get as close as possible to that welfare maximizing price level. So when does that happen? Well, it actually happens precisely when P bar, the dashed line, equals PW. So we should, if we want to optimize welfare, we should set our price cap equal to PW. Perhaps that's not so surprising. We should set our price cap to this optimal PW level, but we should not expect that will induce this monopolist to immediately, as soon as we reach that price cap level, it is going to invest. It will then again wait a bit longer until theta grows bigger and bigger, until the price that's related to that particular theta will hit P star, which is here this minimum level of the black drawn line. That will be the level at which the monopolist will invest. So there will be a regime here, this regime 2, in which still, even under the optimal price cap level, P bar equals PW, there will be this regime in which the monopolist will be waiting will be constrained by this price cap level, will be pricing at the price cap level, but will not yet be investing, and will only do so if theta grows further and further until we actually hit a theta star, which would induce this higher price level P star over here. So of course, as P bar goes up, we see actually that the actual investment level in this extent of this regime in which we are in between the regime 2 essentially grows smaller and smaller. So the larger and larger choose P bar, the smaller this regime 2 gets. So the faster actually the monopolist will switch from being in this constrained regime 2 and make this investment to expand its capacity. On the other side, here's what I just discussed in terms of this analytical thing. So actually, I think 0.05 is the R times I in our case. So I mentioned that as soon as we set our price cap level equal to the cost of capital of investing, R times I, as soon as that happens, actually this P star goes up to infinity, and that's what we see happening. So it actually vanishes off the diagram, it goes off to infinity. And the reason is, let's first discuss what that means. So P star going up to infinity means this monopolist, no matter how high theta gets, it will never reach the investment threshold. So the monopolist will actually never make an investment if we choose our price cap level to be so low as to be equal to Ri, or even lower, of course. Why is that? Well, picture yourself as being the monopolist. You know that the maximum profits that you can make is, well, when you hit the price cap level. So the maximum price that you can get is P bar times K. I can never get more, but I can get actually less. So if theta again drops, well, perhaps I get even below this level. So that means I can, at the most, in certain periods of time, I can get exactly the cost of capital, and there will also undoubtedly be some periods of time when I get a little bit less. So in expectation, I will never be able to recoup those investment costs I of adding any additional capacity. So it will be always a loss-making investment. I can never in expectation be expecting to recover those investment costs, which are Ri in terms of a flow of costs. So that gets us to the conclusions essentially of this paper by Dobbs. That again, so I hope you will understand the way in which the analysis that we did, but this ultimate getting to the bottom of this model and getting the P star as this function of P bar, that's a bit beyond what I am expecting of you for the exam. You do have to know, the method that we use, of course, should look familiar. You should understand this for this paper, and also the qualitative results that I just discussed. They should be known to you for the exam as well, of course. So the optimal price cap that we found is, well, we should set this price cap P bar equal to this welfare optimal threshold PW that we did compute, that you should be able to compute, of course. PW, I did that on paper. So that means that as a regulator, you should take into account the option effect. So you remember this beta, or the beta 1 rather, divided by beta 1 minus 1, that represented basically the option value of this that's inherent in this cap level. So I go back to that PW thing. It was over here actually. So here we have the capital costs, but here we have beta divided by beta minus 1, beta 1 divided by beta 1 minus 1, which is the markup essentially on these capital costs that represents the option value of being able to invest, or being able to wait rather. And as sigma again gets bigger, of course this factor here gets larger as well. So I have to take that into account also as a regulator that's actually maximizing total welfare. So going back to the conclusion here. So also we recognize that as soon as we reach this price cap, well, that's not the moment at which the monopolist is going to invest. So after that, monopolist is going to wait a little bit longer until theta grows a bit higher still, up to theta star, which is congruent with this P star level, which is higher than the PW level. So there is this additional weighting at the price cap before this monopolist is going to be induced to invest. So we do not actually manage to make the monopolist invest at the welfare maximizing threshold just by setting this price cap. So that's the big conclusion that we should take here. The other thing is, of course, we should not expect this monopolist to invest at all if we set the price cap too low. So if we ignore all this option value, actually just set the price cap equal to the cost of capital, R times I, well then no monopolist is going to invest ever, because it will know I cannot earn more than my cost of capital. I can earn less than my cost of capital at all those times at which perhaps demand might drop, theta drops below this theta bar level. Then my total profits will be below RI, so on average I will not earn back this the cost of capital of my investment. So that's the end, that's the conclusion of Dobbs. So we know what we should do if we are a regulator. Except, of course, this might be some other stuff which, if you have additional instruments, if you can perhaps monitor more closely what this monopolist is doing, we can perhaps direct him to invest earlier. Well, that might be a savior here, and there will again be limits to how far you can do that as a regulator. But just setting price caps, that's just not enough to get to the end of this. Okay, thank you. I'll see you next time.